Hello, everyone. Welcome to lab. My name is Tristan. I'm going to be taking over today for Adam. I'm going to give it a minute to let some people join, but then after that, we can dive in. One more minute, and we can get started. So this week is going to be on Grover's algorithm and specifically exploring the Oracle operator. Let's get started. Give me 1 second. All right, I will double check with the ed team to see what the lab attendance code is. It's not, but I will share that by the end of when I'm done. All right, so today's topics are going to be quantum resources in Grover's, Grover's insert, and then oracles. All right, running objectives today is going to be to recognize how to implement Grover's insert for a small problem, and recognize how to build an oracle without knowing the solutions ahead of time. Let's get started. All right, quantum resources in Grover's. So Grover's algorithm in quantum resources. Grover's algorithm is a search algorithm. There is an oracle operator and a diffusion operator. The oracle operator flips the phase of the correct answer, and the diffusion operator makes us more likely to measure the correct answer. Grover's algorithm uses which of the following quantum resources? Does anybody have any guesses? Chat if you do. Interference, yeah. They do use interference. They also use superposition, as with most quantum states. We want our qubits to be able to be in the 0 state and the 1 state simultaneously. So interference is important and specific to Grover's, but it also uses superposition. All right. So here's just a very simple Grover circuit, kind of the steps that we're going to put our qubits through in order for Grover's algorithm to work. The first step, we want to put our qubits into an equal superposition. So here we append an H gate at the beginning to put all the states into an equal superposition. That's the superposition aspect of Grover's that I was talking about earlier. Let's see what the next steps are. Suppose we have one qubit and we want to find the 1 state. So first, we're going to create an equal superposition by applying an H gate. So here we put it into an equal superposition where we have a 50% chance of measuring the 0 state and 50% chance of measuring the 1 state. The oracle will then flip the phase of the correct answer. So we'll go from this state right here, the 1 over radical 2 times the 0 plus the 1, to 1 over radical 2 times the 0 minus the 1 state. So here, what gate is going to be serving as our oracle operator for this specific case? We're flipping the phase of our correct answer. Any guesses on what gate flips the phase of the qubit? Not. So the H gate will put it into a superposition, and then in this case, since it's already in one, it will take it out of a superposition. the gate that'll flip the phase is, that's right, the Z gate. So the Z gate flips the phase computer. So here, our oracle operator is a Z gate. So we take this state on the left is the plus state. We flip the phase, put it into the minus state. Then we have a diffusion operator that makes it more likely to measure the correct answer. In this case, the diffusion operator will bring us to the one state. So here we have the minus state, we apply an operator, the diffusion operator, and it goes to the one state. Does anybody have any guesses what gate will take us from the minus state to the one state? Yes, the H gate is correct. So here the H gate will uses interference to turn the minus state into the state. Right. So let's think about it in another way. So we have another way of visualizing what's happening here that can provide additional insight into what the oracle and operators do. That method is vectors. So for those of you who are more mathematically inclined, who are getting it conceptually or maybe not getting it conceptually and just want to see what the math kind of looks like there, just send it to you. For those of you who understood it conceptually and are a little bit nervous about the math, that's okay. This is mostly supplemental, just to give you another way of looking at it. If explaining the same thing that we just went over, but we're seeing full math behind it. All right. So let's say that we want to find our friend Waldo. There was an issue with the attendance code. I'm going to check to see what it is at the end of lab, and I'll share it with you. But we haven't shared it yet. Right. So let's say we're searching for our friend Waldo over a group of 4 items. So here we have Waldo. I don't know if anyone can remember played Where's Waldo growing up. That's him. Right. So we're looking for him over a space of 4 items. There's Waldo. There's this guy who's a yellow and black version of Waldo wearing sunglasses and a mustache. There's the dog Waldo, and then there's this wizard. So we have this space of 4 people who specifically want to find Waldo. Anybody else is an incorrect answer. So we're going to divide our 4 items into 2 groups. The W for Waldo and the N's for nuts. So Waldo is the only correct answer. The N's, the 3 N's here are nuts. All right. So we can represent W and N with vectors as shown here. They're perpendicular because they have nothing in common. Nothing about N lines up at all with W. And none of these people are Waldo, and all of these people are Waldo. So they're in 2 distinct groups. Okay. So what do we want to do? First, we're going to take a vector that represents the average of all the states. As we can see here, even though it has components of W and N, it is closer to N because right now, if we just took a random measurement, we would be 3 times as likely to measure N as we would measure W. So it is much closer to N than W. Okay. So here, we're going to take a closer look at this vector. So this A vector is all of our states. You see, as I mentioned, it's much closer to W or to N than W. There's a very small component of W here and a very large component of N. Right. So what is the next step? We take our oracle operator and we're going to flip A over the vector N. So think of vector N, this bottom vector here, like a mirror. The new vector A is the reflection. The new vector is vector A's reflection in the mirror. So just flip it directly by N. So if you need to picture this, just look at a mirror, closest one to you, look at yourself in there. You are the vector A. Whatever image you see in the mirror is the new reflection of A. Right. And then our operator will flip or reflect our new vector over our old vector. So this is where it gets a little bit trickier to kind of picture. In this case, rather than N being the mirror, A is the mirror. So it's going to flip all the way from the first reflection that we have in this new spot over here. So this is the result of applying Grover's operator. That makes sense to everyone. It's a little bit tricky, but hopefully the visualization helps. Any objections? So I'm going to keep going. Right. As you can see, flipping it first over n and then back over a brings us much closer to Waldo, which means that if you just took a random measurement now, we're much more likely to measure Waldo than we were for our first vector. It still is a little bit closer to n than to w, so we're going to want to repeat this process. But we can see here we're heading in the right direction. Right. So at the end of one iteration of Grover's algorithm, we do see that the overall state has rotated from A to A1. So the component of W has increased, like I mentioned. So if we keep repeating this process, we'll have a second iteration. We're doing the exact same thing. So here we're going to flip A1 over N, and then we're going to flip the reflection of A1 over the original vector A1 to get A2. And we see that we keep moving closer and closer to Waldo. We can do it again. And after the square root of n iterations, the resulting vector an is closest to w. So n big N here is the number we're searching over. So measuring the state at this point will maximize the probability of measuring w. Now you see here that we're never 100% at w. It's basically impossible to do that, but here we're going to measure Waldo almost all of the time. So in an actual quantum computer, a way to just make sure that this works is just do this measurement multiple times. So you do it 100 times, it comes back 97 times Waldo, then you're going to use that as the correct answer. If it comes back 3 times as one of the knots, you know that those are kind of outliers. What happens if you keep applying Grover's operator for the optimal number of times? Well, what happens is you actually kind of move past this Waldo vector and actually start to become less and less likely to measure Waldo. So it becomes less efficient if you apply it more than radical n times. All right, so that is Grover's algorithm conceptually and mathematically. Now we want to take some time to see how we actually code Grover's algorithm in CERT. Into CERT. So Grover's algorithm, you can basically boil it down to 5 steps. First, you want to define the size of the problem. Then you want to build your oracle. Next, you want to create your circuit. And then you're going to apply Grover's algorithm. Now, almost all the time, you're going to have to keep applying Grover's algorithm because the first time is not the optimal number. So you just keep repeating step, that should be step 4, the optimal number of times until you reach the optimal number. Right. So let's go through these steps. So steps to solving Grover's algorithm. Insert step 1, define the size of the problem. This can look different for each problem, but generally requires some way to encode our problem into qubits. If we want to search over the list of options, then we need to encode each one into its own state we can measure. So here we have 0, 1, 0, 1, 1, 0, 1, 1, and so on. We need to provide rules for finding the answer. And so what will that look like? So here is an example with 2 options. This only requires 1 qubit. So the options could be 0 or 1. An example with 3 options will require 2 qubits. So it'd be 0, 0, 0, 1, 1, 0. So this could represent any 2 options we want. The first example here. So if we're searching for apple and orange, we could say apple is 0, orange is 1. Cat and dog, 0 and 1. Bit in 0 state and bit in 1 state, generally. So once we've encoded the problem, we need some sort of rules for finding the answer. So today, we'll just provide the answer itself. The rule is whether a state matches the answer or not. But in general, oftentimes we'll have to code the set of rules that defines the answer. All right, so let's jump into the coding notebook. we'll complete problems 1.1 to 1.3 together, and then you all can do 1.4. First thing you're going to want to do, let's go here to make sure everything's recorded. Lots to report today. Working part one. So in this part, we will set up the search problem by specifying the number of choices we are searching through and the choice we are searching for. So remember that in a search problem, we know what we're looking for, we just don't know where it is located. So together, let's create a variable named number of choices, set it equal to 4. This is the total number of choices we will search through. And we're going to create a second variable named correct choice and set it equal to 2. This is the number of the choice you're searching for. Right, that's easy enough. So we already have numbered choices, correct choices. So we just want to set this equal to 4. Then correct choice, we're searching for 2. All right, so together, let's determine how many qubits would be needed in Grover's algorithm for the number of choices we need. Anybody have a guess? 4 possible options. How many qubits would we need? So we know that if we had 2 options, we need 1 qubit for the 0 state and the 1 state. If we had 3 options, yes. Yep, that's exactly right, Hannah. We need 2 qubits because here 2 qubits can define up to 4 options. They can also do 3, but 4 options you could have the 2 qubits as 0, 0, 0, 1, 1, 0, and 1, 1. All right. Now, part 3, we're going to run the code below to create binary representation of each of the number of choices that you enter. This is important because these binary representations will then get encoded into the corresponding quantum state. So this is what I was talking about, where the 2 qubits can be used to represent 4 options. That was the 0, 0, 1, 0, 0, 1, 1. So here, we're just going to run this code here. Make sure you run it because, like this section says, if you don't run the code, it's not going to work. Run this code here. All right. And now you guys can handle 1.4 by yourself. Utilizing the provided function, generate a list of ones that contain the binary representations. Or sorry, not ones. Generate a list named ls that contains the binary representation of each of the number choices. All right. So make sure you read through this definition. This will probably help you. Yeah. I'll give you all a minute or 2 to do that. All right, how are we doing? We about done. We need a little bit of time. Seeing we finished. Keep moving. All right. So now the next section is going to be step 2. So we're going to make the oracle. So this is often with Grover's algorithm the most difficult part of actually implementing it. So for now, we're just going to provide the oracle the answer, but later on, we're going to learn more about oracles and how to actually implement them. All right, step 3 for Grover's. This is always putting all qubits into superposition regardless of the problem. This allows Grover's to consider all possible solutions. So when you're creating the circuit, remember the first step is always applying HV to every qubit. So here, circuit equals Grover iterations qubit, comma, ancilla, marked bit string, repetitions. That is going to be for repeating the circuit however many times. All right. So now we're going to jump back into the notebook. So we're going to together do 2.1 to 2.4. Then you all can work on 2.5 and 2.6. Okay, so in this part, we will create the oracle that sets the marked item. The oracle uses an extra qubit called ancilla. You saw that in here, qubits, comma, ancilla. Yeah. All right, so problem 1, first, we're going to run the code below to create the oracle. Then we're going to use it to create the search problem. So as I mentioned, this time we're really just creating an oracle that already knows the answer. But oftentimes, when we're working with, well, pretty much every time when we're working with Grover's algorithm, you're going to have to build an oracle and kind of define how it will find our answer. Let's run this code together. Okay. Then problem 2.2, let's run the code below to create the Grover iteration that comes repetitions of the oracle and the diffuser to the circuit. So here, this does exactly what that said. So you can do it on your own time, but just comments in here. So first, as I mentioned, first step, always create an equal superposition over the input qubits. So H qubit on all of them, put the output qubit into minus state, which is the oracle, and the oracle, and so on and so forth. So it's a bit lengthy, but right now all you need to do is but I do recommend on your own time, definitely read through this, try to understand everything that's going on. A lot of it's a bit complicated, but I think especially with the comments in there, if you take the time to just kind of go through it line by line, you'll be able to understand basically all of it. All right, now 2.3, we're going to initialize the 2 qubit registers. So the qubits here, we're going to create a line qubit of size qubits, and then an named qubit within ancilla. So here we're going to do line qubit qubits, which we set earlier in this problem. So this time we are working with line qubits. I know for most of this course, we have been doing name qubits, which we so but they essentially function the same thing. The line qubits are just going to be a line. They're actually very similar to name qubit.range, exactly the same. You don't have to express too much about it. So at except for two qubits. There we go. 2.4, let's run the code below, prepare a state marked bit string, which converts our choice to a list of bits denoting the binary representation of the number choices, then print marked bit string. All right, so the definition here does exactly what we said. So it's going to prepare a state that converts all of our choices into bits. So let's just run this, right? And then we're setting marked bit string equal to this function, but with correct choice and number of qubits. Correct choice is not defined. What's going on here? I'm pretty sure I did define all this. Maybe I didn't run this. Must not have ran any of the code. Sorry about that. Okay, correct choice. Let's try that again. Okay, and now we want to print marked bit string. Print it. We're gonna get 1 and 0. Yeah. So now problems 2.5 and 2.6, you all can do independently. I'll give you about 4 minutes to work on that. When you finish, please let me know by sending done in the chat, just so I have an idea of how we're all doing. All right. Hopefully we're all about wrapping up. Does anybody need more time with those? Got a few dots in the chat. Okay, So now we're going to move on to step 4, which is applying Grover's algorithm. So here we want to create an amplification problem object. So basically what we're going to do is we have a circuit, and we're going to define this, which will sample from the circuit X number of times, run it over X number of repetitions, and it's going to plot a state histogram with the results showing how many times we measured, or what answers we measured how many times. Then we're going to keep repeating this step until we reach the optimal number of times. And I'll let you guys kind of work through that to find what the optimal number is. Right, so we're going to jump back into the notebook. We're going to do 3.1 together, and then you all will do 3.2 and 3.3. So 3.1, we're going to run this cell below to see the first measurement results. So we have all this. Run it. So it's not defined because I did not define my circuit. Circuit. Okay, so sample results. 0, 1 was measured 258 times, 1, 1, 256, 1, 0, 256, and 0, 0, 254. The most common bit string that we found was 0, 1. So we found a match no. Because if you remember, I believe match, what was the match here? The correct one we wanted 1. So, here. So as you can see, 258, 256, 256, 254 have an equal chance of measuring each qubit. So what we want to do is we want to keep applying Grover's algorithm until eventually the correct answer is much more likely to be measured than the incorrect answers. All right, so I'll give you guys a couple minutes to do problems 3.2 and 3.3. Just like before, let me know in the chat when you're finished, and then we can move on. How's everybody doing with the rover problems? Are we close to finish? Need a little bit more time. One done. Give you all another minute or two. Make sure you send a done message in the chat. Okay. Let's keep moving. Just make sure we have time for the last section. All right, so for those of you who finished, congratulations. You just simulated one of the most famous quantum algorithms. For those of you who just need a little bit more time, recommend on your own, just keep working through it because it is really cool and really rewarding. And this is one of the first opportunities for you all to actually do something that's kind of a useful quantum algorithm. All right, so let's take a closer look at oracles. So some of you might be wondering, did we cheat when we put this together? In practice, we already knew the answer we wanted to find, which made it easy to find the oracle. So how do we find the oracle if we don't know the correct answer? We might not know where our answer is, but we do know some properties of the answer. So going back to our Where's-Waldo example, we can define an oracle that helps us find our friend. So when we're looking for Waldo, we know that we're looking for a person who's wearing glasses, a red striped shirt, and has a cane. So in practice, the oracle is created by knowing the rules of the problem and what is and is not allowed for something to be a solution. So in the Where's-Waldo case, we need to create a quantum circuit that changes the phase of any state representing a person wearing red and white stripes and wearing glasses and has a cane. If you remember in our example, there was a lot of people here that we're searching over that has glasses but didn't wear red and white stripes, or has a cane but doesn't have glasses, and so on. So this way, the oracle just checks each state against these rules and says whether or not it's correct. So now it's time to formally define what an oracle actually is. All right, so key term. So an oracle is a part of an algorithm that can perform a specific computation for free. The trade-off is that we can't know how they do it. So an oracle is like a genie that grants you a computational wish. So here, our oracle, we are asking if Alice's password is 1234. The genie will tell us no. Doesn't tell us how it knows that it's the password or not, but it runs this against the real password and determines no, it is not. So there's a couple different types of oracles. There's decision problems. So given problem, the genie will tell you whether the answer is no or yes. So that's the example we just went over. Is Alice's password 1234? It's a no. But there's also function problems. So given an input, the genie will calculate the output of some unknown but desired function. So here we have, what is the function of 0, 1, 1, 0? And the oracle will tell us 6. Don't know what the function is, don't know how to calculate that. but we do know that it was able to provide us with the answer. All right, so how do we create an oracle that's able to do those things for us? So first, we want to define the rules. So the main difficulty is defining the rules, figuring out how to frame a problem in a way that this oracle understands is a puzzle that needs to be solved in each case. So this happens a lot in computer science. We often have the algorithm already, but we need to figure out how to frame our problem in a way that the algorithm can understand. So for example, we need to use a specific language here to define our problems. So the first thing we need to do to be able to solve these puzzles is to familiarize ourselves with the language used. In this case, it's a series of logical statements involving the following options. So here we have some symbols, so not, and, or, XOR. So the inputs here are going to be 1 bit for not, 2 bits for and, 2 bits for or, and so on. So here, for not, output false when the input is 1, outputs true when the input is 0. For and, it's 2 qubits. So false when the input is 0, 0, 0, 1, 1, 0, true when it's 1, 1, and so on. You can see that we have a specific language here that we're trying to code into bits. And so all the outputs will tell us whether or not something is false or true. Okay. So defining rules, examples. So let's see some examples of what this would look like. So here we have an example A and B. So it outputs false when A and B is 0, 0, 0, 1, 1, 0, and outputs true when it's 1, 1. So you see here that it has to be yes, A, and yes, B. So in this first example, it's neither A nor B. Here it's just B, and here it's just A. So it's only true if it's both A and B. Next, we have outputs false when it is A and B. So this is not A and B. So it's only false when it's both A and B. It's true any other combination. So here, A and B, or not A and not B. So it's never false. So it's never going to output false. It's always going to output true. So this covers the entire spectrum of possibilities. All right. That was a lot of information, this lab. So really quick temperature check to see how people are feeling. How is everyone doing? It's all right if it's a little low, as I mentioned. I think this was a lot of information. Also, feel free to send it directly if you want to share in the big group. How are people doing 1 to 5? Fours. Mostly fours. Okay. Are there any specific questions? Understanding. Anything we can do to help? Is it just that you all think you might need some more practice with Grovers? Totally understandable. It was definitely one of our more complex labs this week. So if you just feel like you need a bit more practice to get used to it, totally fine. Are there any specific questions? If not, that's okay. I always assume that in order to get from the 4 to the 5, you always think a little practice. Okay. Yeah. So that was this week's lab. I do recommend with your own time, just make sure that you keep going through that notebook. It's a very useful notebook, definitely a lot of information in there, a lot of things you can just break down. So I do recommend looking through that just to really enhance your understanding. I think for those of you who were at fours and lowers, just reading through the code would be very useful, really help you understand what's going on with Grovers, really understand each step more intricately. But the big thing here is just take away the concepts of Grovers, understanding basically how it's implemented, understand how it works. The minute detail is less important, but if you want to kind of get into that next step, going through the notebook itself will be the best way to do it. I am still waiting on the attendance code. So unfortunately, you all are going to have to stay on a little bit longer, but hopefully that will be coming soon. No, the attendance code is what we're waiting on now. Unfortunately, wasn't added to the lab slides prior to lab. So I reached out to programs team to have somebody share that with me, but it's shared that yet. I did notice there's no lab attendance for the quiz, which makes me wonder if there isn't a lab attendance code currently, but I know that there is supposed to be. So it'd just be an oversight, so I'm not going to tell you all to leave, because I do assume that a lab attendance quiz is going to be created, with a lab attendance code. And hoping that code will be coming shortly. Okay, we are nearing the end of the scheduled lab time. We still haven't gotten a attendance code, so my recommendation would be rather than you all staying on for an extra, who knows how long this will take. Just watch the lab recording later, fast forward to the end, because that's where the code's going to be at this point. They might just send it out to you, but if you don't get the code in the next day or so, I would recommend watching the lab recording. Sorry all for the technical difficulties, and thank you for coming to lab. I'm gonna stay on in the recording just until they share, but you all can sign off for coming for the rest of your day. Okay, just got the lab attendance code. So this week's lab attendance code is 1536. 1536. Sorry, everyone, for the delay, but that is the lab attendance code this week, 1536. Great. Thank you all for joining lab. Take care.